If you are studying for your grade 12 physics final exam right now, stop everything and watch this video. Because this question, electron trajectory between charged plates, shows up on almost every exam. And most students drop marks on it for one reason. They forget one tiny thing about where the electron enters. I'm going to show you exactly what that is. But first, let's make sure you understand the whole problem from scratch. Hey everyone, welcome back. In today's video, we are going to fully solve the electron trajectory between charged plates problem, step by step, including a full diagram walkthrough so you can see exactly what's happening before we touch a single formula. By the end of this video, you will know all 5 steps. You'll understand why each formula works, and you'll know the number 1 trap that kills marks on this question. Let's go. Here is the problem. An electron enters horizontally between 2 parallel plates. The plates are separated by d equals 4 centimeters. There is a potential difference, a voltage of 200 volts across them. The plates are 8 centimeters long, and the electron enters midway between the plates, moving horizontally at initial velocity. V0 equals 3 times 10 to the 7 meters per second. We are given d equals 0.04 meters, V equals 200 volts, L equals 0.08 meters, V0 equals 3 times 10 to the 7 meters per second. The electron mass M equals 9.11 times 10 to the negative 31 kilograms, and the electron charge Q equals 1.6 times 10 to the negative 19 coulombs. On your exam, before you do anything else, write these values down and convert centimeters to meters right there. D equals 0.04 meters, L equals 0.08 meters. Don't leave them in centimeters and plug them in. That's how you make unit errors. And notice this warning already. The electron enters mid-gap. We'll come back to why this matters a lot in step 5. Keep that in the back of your mind. We need to find 3 things: the electric field, E, the vertical acceleration, A, and the vertical deflection, Y, and whether the electron hits a plate before it exits. Before we solve anything, let's look at the diagram. This is the single most important thing you can do on an exam. Draw the picture first. So let me walk you through exactly what is happening physically. Up here at the top, the red plate. This is the positive plate. You can see the plus signs along it. This plate is connected to the positive terminal of the battery, so it has a buildup of positive charge. Down here at the bottom, the blue plate. This is the negative plate, the minus signs along it, connected to the negative terminal, opposite charge. Now, between the 2 plates, we get a uniform electric field. These yellow arrows show it. The electric field always points from the positive plate to the negative plate. So the field is pointing downward in this diagram from the red plate down to the blue plate. This field is the same strength everywhere between the plates. That's what uniform means. It doesn't matter if you're near the left edge or the right edge or the middle. The field strength is the same. That's one of the key properties of parallel plates. Now, here comes our electron, the cyan dot on the left side. It enters from the left, midway between the plates, exactly halfway, equal distance from the top plate and the bottom plate. The electron enters moving horizontally to the right. That's V0, the horizontal velocity, shown by this arrow on the left. Now, the moment it enters the plates, something interesting happens. The electric field exerts a force on the electron. But wait, the electron is negatively charged, and the electric field points downward. So what direction does the force act on the electron? Upward, opposite to the field direction. Because the electron is negative, it feels a force opposite to the field. So it gets pushed toward the positive plate, which is the top plate in our diagram. That's exactly what you see in this curved path. The electron enters horizontally and then curves upward toward the positive plate as it travels across. By the time it reaches the right edge of the plates, it has moved upward by some vertical distance. That distance is what we call Y, the vertical deflection. That's what we need to calculate. The horizontal distance it travels is L, the plate length, 8 centimeters. The electron crosses this entire length horizontally while being deflected vertically at the same time. The total gap between the plates is D, 4 centimeters. The electron enters at the midpoint, so it is 2 centimeters from the top plate and 2 centimeters from the bottom plate. This dashed line shows the mid-gap entry point. This is crucial. If the electron deflects more than 2 centimeters upward, it hits the positive plate. If it deflects less than 2 centimeters, it safely exits on the right side. So the question is, does y end up greater than d over 2, which is 2 cmm, or less than it? So to summarize the diagram, electron enters left, mid-gap, moving horizontally. Electric field pushes it upward. It curves toward the positive plate. We need to find how much it curves and check if it hits the plate or exits safely. Now that you can see what's happening, the maths becomes much easier. Let's solve it. Before we jump into formulas, I want to give you the insight that makes this entire problem click. Look at the diagram again in your head. The electron moves horizontally at constant speed because there is no horizontal force, and it accelerates vertically because the electric force acts vertically. Does that sound familiar? That is exactly what happens in projectile motion. When you throw a ball off a cliff, it moves horizontally at constant speed, and gravity accelerates it downward. Here, the electron moves horizontally at constant speed, and the electric force accelerates it upward. Same structure, same equations. Horizontal, constant velocity, use distance equals speed times time. Vertical, uniform acceleration, use y equals half a t squared. The only difference is that instead of gravity causing the acceleration, it's the electric force. And instead of 9.8 meters per second squared, we get an acceleration that is 90 trillion times bigger, which is why gravity is completely ignored in these problems. Once you see this analogy, you never forget it. This is projectile motion with electricity. All right, let's solve. Step 1. Find the electric field. Between parallel plates, the electric field is uniform, and the formula is E equals V over D. Voltage divided by plate separation. Plug in E equals 200 volts divided by 0.040 meters. E equals 5,000 volts per meter. You could also write this as 5,000 newtons per coulomb. Same unit, just expressed differently. Quick units. Check. Volts per meter equals newtons per coulomb. If your teacher asks you to verify units, that's the equivalence. And the direction of this field, from the positive plate to the negative plate. In our diagram, that's downward. We'll need this direction in the next step. Step 2. Find the force on the electron. The formula is F equals QE. Force equals charge times field. F equals 1.6 times 10 to the negative 19 coulombs times 5,000 newtons per coulomb. F equals 8 times 10 to the negative 16 newtons. Now, this is where people make mistakes. What direction is this force? The field, E, points downward from positive plate to negative plate. If we had a positive charge, the force would also be downward in the same direction as E. But we have an electron. An electron has negative charge. So the force is in the opposite direction to E. The force on the electron is upward toward the positive plate. Think back to the diagram. The electron curved upward. That's why the electric force is pushing it toward the positive plate at the top. Every time you do a problem like this, ask yourself, positive charge or negative charge? If negative, flip the force direction. Always. Step 3. Vertical acceleration. Newton's second law, F equals ma, so A equals F divided by m. A equals 8 times 10 to negative 16. Newtons divided by 9.11 times 10 to the negative 31 kilograms. A equals 8.78 times 10 to the power of 14 meters per second squared. Let's just appreciate that number for a second. 8.78 times 10 to the power of 14. Compare that to gravity, 9.8 meters per second squared. The electric acceleration is roughly 90 trillion times stronger than gravity. This is why, in all parallel plate problems, we completely ignore gravity. It contributes essentially nothing compared to the electric force on an electron. So our vertical acceleration is 8.78 times 10 to the power of 14 directed upward toward the positive plate. Step 4. How long does the electron spend between the plates? Go back to the diagram. The electron travels horizontally across the entire plate length L, and horizontally, there is no force, so it moves at constant speed v0 the whole time. So, time distance divided by speed. T equals L over v0. T equals 0.088 e meters divided by 3 times 10 to the power of 7 meters per second. T equals 2.67 times 10 to the power of negative 9 seconds. That's 2.67 nanoseconds. Incredibly fast. I want to flag the most common mistake on this step. Students sometimes try to use the vertical speed or the final speed in this formula. Don't. The v0 here is the horizontal entry speed, because we're calculating how long it takes to cross the horizontal distance, L. The horizontal speed never changes, no horizontal force, so v0 stays constant the whole way across. Step 5. The final calculation and the most satisfying one. How far does the electron deflect vertically while it's inside the plates? The electron starts with 0 vertical velocity. It entered purely horizontally. So we use the kinematics equation for uniform acceleration starting from rest. Y equals half times a times t squared. Y equals half times 8.78 times 10 to the power 14 times 2.67 times 10 to the power of negative 9 squared. Let's work out t squared first. 2.67 times 10 to the power negative 9 all squared equals 7.13 times 10 to the power negative 18. Now, y equals half times 8.78 times 10 to the power 14 times 7.13 times 10 to the negative 18. Y equals 3.13 times 10 to the power negative 3 meters, which is 3.1 millimeters. So, the electron deflects 3.1 millimeters upward. Now, the big question. Does it hit the plate? This is the moment I mentioned at the start, the thing that kills marks. Remember the diagram. The electron entered midway between the plates. The total gap d is 4 centimeters. So, the electron started exactly 2 centimeters from the top plate and 2 centimeters from the bottom plate. The electron is curving upward toward the positive plate. So the question is, does it travel more than 2 centimeters upward before it exits? The maximum deflection before hitting the plate is d over 2. Not d. d over 2. 2 centimeters. 20 millimeters. Our deflection, y equals 3.1 millimeters. Maximum allowed equals 20 millimeters. 3.1 is less than 20. The electron exits safely. It does not hit the plate. Now imagine a student who used d equals 4 centimeters as their limit instead of d over 2. They'd compare 3.1 millimeters to 40 millimeters. They'd still get the right answer here, but change this problem slightly. Give it a higher voltage, a shorter plate length, and y might be, say, 25 millimeters. If you use d equals 40 millimeters as your limit, you say it doesn't hit. If you use d over 2 equals 20 millimeters, you correctly say it does hit. That's the difference between full marks and losing marks. Always, 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 always use d over 2 when the electron enters mid-gap. Say it with me, d over 2. Let me show you all 6 formulas you need for this type of problem. Everything on one slide. Number 1. E equals V over D. Electric field between parallel plates. Simple ratio. Number 2. F equals Q E. Force on the charge. Remember to flip direction for electrons. Number 3. A equals F over m. Newton's second law. Vertical only. Gravity ignored. Number 4. T equals L over B0. Time in the plates. Always use horizontal speed. Number 5. Y equals half times A times T squared. Vertical deflection. Kinematics from rest vertically. Number 6. Compare y to d over 2. The hit check. If y is greater than or equal to d over 2, it hits. If y is less than d over 2, it exits safely. Screenshot this slide. Stick it above your desk. These 6 things are your entire toolkit for this question. Let me give you the full 5-step process one more time, nice and clean. Step 1. E equals V over D. Find the electric field. Step 2. F equals Q times E. Find the force. Flip direction for electrons. Step 3. A equals F over m. Find the vertical acceleration. Step 4. T equals L over B0. Find the time using horizontal speed. Step 5. Y equals half times A times T squared. Find the deflection. Compare to D over 2. And the 3 traps, write these down. Trap 1. Use D over 2, not D, for the maximum deflection. The electron enters mid-gap. Trap 2. Flip the force direction for electrons. Negative charge means force is opposite to E. Trap 3. Use the horizontal entry speed, V0, for time, not the vertical speed. And our final answers for this specific problem. E equals 5,000 volts per meter. A equals 8.78 pi, 10 to the power of 14 meters per second squared. Y equals 3.1 millimeters. The electron exits safely because 3.1 millimeters is less than D over 2 equals 20 millimeters. That is the complete solution. Diagram, analogy, all 5 steps, and the exam trap fully explained. If this video helped you, please hit the like button. It genuinely helps other grade 12 physics students find this content when they need it most. Drop a comment below if you want me to cover the next hard unit question, charged particles in a magnetic field, velocity selectors, or field superposition. I'll make whichever one gets the most requests next. Subscribe if you're prepping for the grade 12 physics final. There's a lot more coming. Good luck on the exam. You've got this!